Welcome back, listeners, to another episode of Operating Systems Crashcast. I'm your host, Victor, and with me, as always, is the brilliant Sheila. Today, we're wrapping up our chapter on CPU scheduling with a comprehensive summary. Sheila, are you ready to dive in?
Absolutely, Victor. I'm excited to recap this crucial topic. CPU scheduling is at the heart of multitasking operating systems, and understanding it is key for any aspiring OS engineer or computer scientist.
You're right, Sheila. Let's start with the basics. Can you remind our listeners why CPU scheduling is so important?
Of course, Victor. CPU scheduling is essential because it determines how processes share the CPU in a multitasking system. Think of it like a busy restaurant kitchen with multiple chefs and limited cooking stations. The scheduler is like the head chef, deciding which dish or process gets to use the stove, CPU next. This affects everything from system performance to user experience.
That's a great analogy, Sheila. Now, let's recap some of the key scheduling algorithms we've discussed. Can you start us off with the simplest one?
Certainly. The simplest algorithm is first come, first served, FCFS. It's exactly what it sounds like. Processes are executed in the order they arrive. While it's simple, it can lead to the convoy effect, where short processes get stuck behind long ones, like being stuck in a slow-moving line at the grocery store.
Excellent explanation. To address that issue, we have the shortest job first SJF algorithm. This one prioritizes the process with the shortest execution time. It's optimal for minimizing average waiting time, but it can lead to starvation of longer processes if short jobs keep arriving.
That's right, Victor. And to prevent starvation, we have the round-robin RR scheduling algorithm. It's like a game of musical chairs. Each process gets a small time slice or quantum, and if it doesn't finish, it goes to the back of the queue. This ensures fairness but can lead to high context switch overhead if the time quantum is too small.
Great point, Sheila. We also discussed priority scheduling, where each process is assigned a priority. This can be effective, but may also lead to starvation of low-priority processes. To mitigate this, some systems use aging, gradually increasing the priority of processes that have been waiting for a long time.
Absolutely, Victor. And for more complex scenarios, we have multi-level queue scheduling and multi-level feedback queue scheduling. These algorithms divide processes into different queues based on characteristics like priority or type, and may even allow processes to move between queues.
Excellent summary, Sheila. Now let's talk about how we evaluate these scheduling algorithms. What are some key criteria we consider?
Great question, Victor. We typically look at several metrics. 1. CPU utilization. We want to keep the CPU as busy as possible. 2. Throughput. The number of processes completed per unit time. 3. Turnaround time. The time from when a process is submitted to when it completes. 4. Waiting time. The total time a process spends waiting in the ready queue. 5. Response time. The time it takes from when a request was submitted until the first response is produced.
Those are crucial metrics, Sheila. It's worth noting that the importance of each metric can vary depending on the system's purpose. For example, a batch system might prioritize throughput, while an interactive system would focus more on response time.
Absolutely, Victor. And that brings us to an important point. There's no one-size-fits-all solution in CPU scheduling. Real-world operating systems often use a combination of these algorithms or variations of them to meet specific needs.
That's right, Sheila. For instance, Linux uses a complex scheduler called the Completely Fair Scheduler, CFS, which aims to give each process a fair share of CPU time. Windows, on the other hand, uses a priority-based, preemptive scheduling algorithm with dynamic boosting of priority based on various factors.
Excellent examples, Victor. It's fascinating to see how these theoretical concepts are applied in practice. Now, as we wrap up this chapter, what would you say are the key takeaways for our listeners, especially if they're preparing for interviews?
Great question, Sheila. I'd say the most important things to remember are 1. Understand the basic scheduling algorithms, FCFS, SJF, round-robin priority, and their pros and cons. 2. Know the evaluation criteria for scheduling algorithms and how they apply to different types of systems. 3. Recognize that real-world schedulers are often complex and combine multiple approaches. 4. Understand the concepts of preemptive versus non-preemptive scheduling. 5. Recognize the challenges in scheduling, such as starvation and the need for fairness. 6. Appreciate the impact of scheduling on overall system performance and user experience.
Those are excellent points, Victor. I'd add that it's also important to understand the concept of context switching and its overhead. While not directly a scheduling algorithm, it's closely related and can significantly impact scheduling decisions.
Absolutely, Sheila. Context switching is indeed crucial. It's the process of saving the state of a process or thread so that it can be restored and resume execution later. The time taken for context switching is overhead, so schedulers need to balance the benefits of switching with this cost.
Exactly, Victor. And that ties back to our discussion of the time quantum in round-robin scheduling. A smaller quantum provides better responsiveness but increases context switch overhead, while a larger quantum reduces overhead but may make the system less responsive.
Great point, Sheila. As we conclude this episode, I think it's clear that CPU scheduling is a complex but fascinating topic. It's a perfect example of the trade-offs and optimizations that make operating systems so interesting to study and work with.
Absolutely, Victor. And for our listeners, remember that understanding these concepts isn't just academic. It can help you optimize your own programs and systems, and it's crucial knowledge for any OS-related interviews or work.
Well said, Sheila. And with that, we'll wrap up our episode and our chapter on CPU scheduling. Thanks for joining us, listeners, and stay tuned for our next episode where we'll be diving into the world of deadlocks. Until then, keep your processes running smoothly.
Goodbye, everyone, and happy scheduling.